This is our circuit for Project 2, Waveforms, and Photons. What we have is a voltage source coming through our green wire connected to our GP22 pin and our circuit. Our circuit is simply a 10 kilo ohm resistor in series, which is then connected in parallel to three separate paths. One path is the blue path, or the blue wire, which is connected to our ADC0 channel, which measures the voltage at this point, at the intersection between the three parallel paths. Next, we have a capacitor, which we use to dampen some of our signal later. And we have a 10 kilo ohm resistors. These two paths are then connected into this black wire, which is connected to our local ground. So what we'll be testing first is how we measure the voltage at the parallel junction if our input wave is a sawtooth wave. That means that our voltage wave is a sawtooth wave. How we do this is we come to our code and we see this which one variable. We'll be changing this throughout the demonstration, but if we want to see the sawtooth wave, we keep it to linear. We save, and then we plot. And we see two graphs. The green graph, or the green line, corresponds to the path or the voltage coming through the green wire. All this is in ADU units, but we just see some nice sawtooth wave. It ramps up, reaches the maximum value, and drops. And we see, since these are all linear elements, that the same thing happens at the parallel circuit, or the parallel part of the circuit. We have a clean increase in our voltage, and then once it hits the value corresponding to the max value it can hit, it then drops down. Now, the next part we tested was what would happen if we changed or exchanged our 10 kilo ohm resistor in the parallel circuit, this one right here, with an LED. Well, we'll show that off right now. And we'll be using a red LED for this demonstration. Right here. First up, we can just see that it doesn't light up, and after some time, it lights up. Again, one more time, no light, then lights up slowly. If we want to see explicitly what's happened, we can go to our code, and we'll comment out our previous plot that we had, and we'll just print this new plot, which will print the voltage in, the voltage out, and then the current through the LED. Save, and then plot. Again, we have three lines. We have the green line, which is, again, our voltage into our circuit. The blue line, which is our voltage at the point of the parallel junction. And we have our orange line, which corresponds to the current at the LED. So again, it's a little much like we saw just physically. We have it, if we look at the current through our LED, there's a period of the time where there is no current flowing through. Basically, there's not enough voltage difference to then light up the LED. Once we reach that threshold voltage, that forward voltage, then the LED slowly starts to light up. And it just repeats and repeats. Now, the next part we tested is what would happen if instead of having a sawtooth wave, we had a sinusoidal one. So again, what we do is we go to the switch one variable, take the sinusoidal one, which is the middle one, paste it here, and then save. So let's look at the LED now. We see that it goes on and off, and brightness is controlled, going in a kind of sinusoidal-like thing. Now, to be certain that it's sinusoidal, we can look at the plot of the voltage in. This is just making sure that our voltage wave is sinusoidal in nature. We could also plot the voltage out at the parallel junction, and it would also show the sinusoidal in nature, but it would be much less pronounced, or the voltage part at that point. But again, we just see a sinusoidal wave. If we want to time the sinusoidal wave, we can go to our sinusoidal code, and I have four little lines that I've commented out. This is just to measure the period. We'll do that now. This will be the period for one pulse. going to break our loop. We save, and then we look at the serial, and it'll print out at the very end. 5 seconds, which is the period that we wanted to have. Lastly, the last thing we did was we configured it such that our voltage pulse was a step function, basically. It's a step wave. So it's going to correspond to an on and off pulse. This one directly corresponds to which one having a value of constant. Let's copy this. And we saved here. So we see that the LED is pulsing on and off as we wanted. Now we use this kind of behavior to then get a calculation for approximately the number of photons that are coming from this LED that will reach our eye, depending on where we are, how far away we are from that LED. We use some approximations, assuming that we're at an 80-degree angle away viewing the LED, as well as there being a 1% chance for the photons to actually get emitted from the electrons that are going through the LED. And we can actually see it, and we plotted the distances here. So let me save to run the code again. And we see this plot. Depending on the distance that we're at, we get a number of photon flux. This is the photon flux that we have. And we see that it starts off pretty well, and then there is a 1/r² dependence. So the farther away we are, this is a double, an increase, it drops by 1/4. And so on, and so on. All the way down to being 40 meters away. We still get some number of photons, but much less. And that's all we did for the circuit in this project. Thank you for your time.